All right, this is the first day of 1.5. We're splitting this objective over 2 days. The topic is complex numbers, and as we go through this, if you're feeling perhaps that this content is maybe a little bit of a deviation from linear equations and coming up with linear functions from a point and a slope, you'd be correct. Because it is. We are changing directions a little bit. What's going on is we're starting to move from linear functions to quadratic, and you'll see in time that complex numbers don't have a ton to do with linear functions. They can come up quite frequently with quadratics, which is where we're headed. So we kind of are shifting gears in 1.5. Still talking functions, still talking coordinate grids, just kind of starting to move to a different type of function that needs a few different pieces of algebra to work with it. Okay, the notion of a square root. Okay, a number that's multiplied by itself. That's we're kind of working backwards to figure out what that is. And in this first example here, the square root of 25 is 5 because 5 times 5 is 25. Okay, that's what we call a perfect square. Now, we can take a non-perfect square, and we can do some simplifying with that as well. For example, I can simplify the square root of 24 because it can be split up into factors of 4 and 6. I picked 4 and 6 because 4 is a perfect square, and then I could simplify it to 2 square root 6. Which leads us to the square root of negative 24, okay? Things are a little bit different here because we have to go outside the real number system to answer the question of what is the square root of negative 1, okay? The real numbers, okay, are not sufficient to give us an answer to the square root of negative 1, so we had to go to an imaginary number such as I, okay? The best approach to take here is always just get that negative 1 taken out and then simplify your radical as a positive number. Okay, now we already simplified the square root of 24 as 2 square root 6, but now I can just tag an I on at the end because the square root of negative 1 is always I. Okay, that's the key as we mention that down here. The key is always to get that negative sign taken out. Very important to do that because when we do that, we know that this I is going to show up in the end. But once that negative is out, it always puts us in a position where we can simplify the square root of a positive number, which is something we have much more experience doing at this point in time. Alrighty. Let me get rid of this. Make sure I'm on the correct slide. Here I am. The Fab Powers, the Fab 4 powers of I. Okay, we're now looking at different powers, and specifically we just have to look at the first 4 because you're going to see a pattern that repeats. Okay, now we have already stated here that the square root of negative 1 is I, and I to the first power is just I. Okay? Now, I squared could be written as the square root of negative 1 times the square root of negative 1. And anytime we take a square root times a square root of the same quantity, the answer is just whatever that quantity is. Okay? That means that I squared, I'll put this one over to the side as well, I squared is negative 1, and as we work more with simplifying expressions that have imaginary components to them, that becomes really significant. And it goes to show that you shouldn't think about imaginary numbers as completely separate from real numbers. They are very much related. Okay, it's important to keep that in mind. And that shows us there with I squared equaling -1 that, we take I, multiply it by itself, and that is actually equal to -1, which is a real number. So let's take I to the third, and let's split it up as I squared times I to the first. Well, we have already shown that I squared is -1, and I is just I, which means that I to the third power, in fact, equals -I, as I times -1 is -I. Okay? I to the fourth power would be I squared times I squared. And again, I have already shown that I squared equals -1. And -1 times -1 is just +1. Okay? Those are the four that you need to know because this pattern then starts to repeat. I to the first is I to the sixth ends up being -1, I to the seventh is -I, and I to the eighth is 1. So when I go down to something like this, I to the 15th, what does that equal? It becomes all about multiples of 4. Okay? Now when I look at that, I can tell you right away that I to the 15th power equals -I. And here's why I can do that. I notice with the exponent to the 15th power that it's 1 less than a multiple of 4. The next multiple of 4 would be 16. Okay? Well, I saw that I to the fourth power is 1. Okay? So 1 less than a multiple of 4 would follow I to the third, which is equal to -I. Okay? Let's look at one more. I to the 34th. Again, what I'm after here is where is the closest multiple of 4? That would be 36. Okay, 36 is a multiple of 4. 34 is 2 less than that multiple. Okay, so had it been I to the 36th, that would have equaled 1. I to the 35th would equal -I. I to the 34th power is equal to -1. Okay? Remember these four. This pattern that repeats. I didn't go through and illustrate with exponents that the next four, powers 5 to 8 follow the pattern. They do. If you feel like you need some convincing there, you could certainly do the same pattern I did with taking terms and breaking them down as properties of exponents. For example, if you took I to the 5th, you could break that down algebraically and look at it in terms of I to the 4th times I to the 1st. Okay? That's how you would break those down, and again, you would see that this pattern of 4 continually repeats. All right, I want to jump down here because I want to look at some operations with complex numbers, in particular addition and subtraction. Okay? When we are doing addition and subtraction, we will see that complex numbers are written in the form a plus b times I. They have a real component and they have an imaginary component, and we can really treat this like terms. Okay? I is not a variable, but many times when we're simplifying expressions with I, we can treat it like one. Okay, so we could, if it helps in this first example, that you could kind of pretend that I is, like X, and you would simplify it just like a variable expression. But again, understand I is not it's not a variable by any means. All right, we can just think of it as one. So here I am going to combine my real components. 5 plus 3 is 8. And -4 plus 8 is +4. So that would simplify to 8 plus 4i, which gets me this form I was referring to before. Okay? And that's the form I want my answer. That's what I'm looking for. That's a complex number. It has a real component of 8 and an imaginary component of 4i. On this last example, be careful of parentheses. if I want to start combining like terms, I need to distribute this negative sign, which will make that minus 16 and plus 12i. Once that is gone, then I'm free to just simply combine like terms, like 34 and 16. This is 34 minus 16. That'll be 18. So the real component of this number is 18. And 21i plus 12i ends up being plus 33i. And again, notice this gets me back to this a plus bi form that I want. Looks just like this and just like that. Many times when we're doing operations with complex numbers, if we can get to that form, a plus bi, that's how we know that we're done simplifying, because there's nothing more I can do at that point in time. The imaginary component cannot be added to the real component. Okay, they're two separate numbers from two separate number lines, one from the real number line and one from the imaginary. Okay? Well, I think that is all for day 1 of 1.5. As always, make note of any questions or something, anything you need clarification on. So you're sure to ask on that next time we see each other in class. And we will pick up in day 2 in 1.5, looking at multiplication and division with complex numbers. All right? Again, be sure to ask any questions you have in class.